Hey everybody, hope you guys are doing great here. We're going to finish up the notes real quick on our first target of experiments. So in our last class, we started to talk about the flow chart, the design of experiments, and we finished the class talking a little bit about best practices for experiments. So you'll notice here we drew this experiment talking about what consequences drunk drivers should receive, to see if maybe one consequence in particular has a little bit more effect of deterring them or correcting that behavior so that they don't do it again. And we drew this same flowchart on the other page. This is kind of the official diagram from the book. But you'll notice that there are 3 different paths that individuals could potentially take before we compare how many arrests they have in the following year. Now, ideally, you would want the number of people going into each treatment to be about the same. And here we have 80, 98, and 122. They aren't quite as balanced as we would maybe like. So how did they arrive at these numbers? Well, one good thing that they did do is they randomly assigned people to each group, group 1, 2, and 3. And as we know, sometimes randomness doesn't always lead to nice, even amounts. Now, the paragraph down below kind of describes this situation. It's probably not practical to wait until we can get 100 subjects in each group, and that's a little bit because the treatment must be assigned immediately after the subject's arrest from drunk driving. So statisticians use a table of random digits or a random number generator in order to push each individual into a specific treatment. So we're going to be using a table of random digits. That way we can kind of control, myself here as a teacher, what answers we're getting out. In the real world, you'd probably just use a calculator. So we're going to learn how to do this. If you look at your table of random digits, which was from a few chapters ago, and you can really start at any row reading off singular digits here potentially, because we are going to represent each different potential treatment by the number. Treatment 1, treatment 2, treatment 3. And I'm going to show you a little bit about what would happen if we just started at a singular line. Say maybe we chose line 107 on our table. If we just use 1s, 2s, and 3s, it's going to take us forever to kind of get through assigning people. So if we only look at 1s, 2s, and 3s, you'll notice like 8 shouldn't work, 7 shouldn't work, 9 shouldn't work. And out of the 5 first digits in that table of random digits, we only have 2 successful placements. Somebody's going to treatment number 2, somebody's going to treatment number 3. If we keep going in this second batch, you'll notice nobody gets assigned because you have 5 different digits that are not 1, 2, or 3. And as you go through the whole first line, I've underlined the digits that would be acceptable, and it only gives us 11 people in the end. Now, there are 40 digits in that full line, so only having 11 out of 40 isn't a very good use of our time. In order to make this maybe a little bit quicker, a little bit more efficient, we can do kind of a neat little trick. So down below this, what if we started to group the numbers and let multiple digits represent one particular treatment? Okay, right here. If we let the digits 1, 2, and 3 represent maybe treatment number 1, and maybe 4, 5, and 6 indicate the second option, and 7, 8, and 9 signal the third treatment, it might go a little bit faster. What we're going to do, though, since we have 10 total digits, 0 through 9, is we're going to ignore the digit 0. It doesn't push anyone into one of the particular treatments. But this is a lot better than having, 8 be an extra, 7 be an extra, 9 be an extra, 5 be an extra, 0 be an extra. We have all those extras. Now we're using our digits maybe a little bit more smart. So down below, we have this example to kind of show what we're doing here. 0 through 9 are all the possible digits on the table that we could achieve, and we're going to group them. 1, 2, and 3 group together, 4, 5, and 6 group together, 7, 8, and 9. So if I come across any of those numbers, I know exactly where to put that individual. Now the numbers along each branch, each path of that experiment were achieved using this method. And you don't necessarily have to go 1, 2, and 3, 4, 5, and 6 and group them like that. Potentially, you could have done 1 and 4 and 7, 2 and 5 and 8, 3 and 6 and 9, but that gets a little bit more confusing because your numbers are kind of spaced out a little bit more. So minimize a chance that you're going to make an error. Now, if you're being fair, you probably want a proportional or an even chance for people to get placed in any of the 3 treatments. That's why we have an equal amount of numbers in each group. Let's go through the process of what they actually did to assign people. So the first subject that came in to this experiment got assigned the digit 9. That's the first number in line 105. And so they went to treatment number 3 because that's where 9 was grouped. The second person got assigned this digit, 5. 5 happens to be in this second group, and so they got assigned to the second treatment. Then we went to the third digit. Third digit was also a 5, so this third individual was assigned to that random number, which pushes them to that second treatment group. The fourth individual, I think, was a 9 again. 9 happens to be group number 3 in the end. And then the last digit in that little clump is the digit number 2. So that fifth individual who's caught drunk driving, they got assigned the second digit, which pushes them into the first group. So all the way back up here, they're going to be the control. Wasn't an extra punishment after they had their fine and some jail time. So you would just keep on going throughout the row and assigning people based on these numbers. But something happens here as we kind of progress along. There are a couple of zeros. So you'll notice 0 happens between 4 and 7 in that line. And so here in our little table recording what happened, 4, there would be a 0 here, there'd be another 0, and then the next person would get the digit of 7. So they don't actually record the digits 0 at all. They just ignore them like what we set up in the paragraph above. So we would do that until we got all 300 people assigned to one of the groups, or we'd keep track as they came in. We'd just go to the next place on the table and then put them in a group based on that. That way we're not being biased. We aren't saying, ooh, I don't like you, so let's put them in the worst group. Or, oh, that's my friend, so we're going to put them in the control group. That would be biased, and that would not be a well-designed experiment. So by the end of row 105, we've assigned 10 subjects to treatment 1, 9 subjects to treatment 2, and 18 subjects to the third treatment. You can see they're not all equally placed. But hopefully as you get more and more people, it will start to even out a little bit. At least it's fair in the terms that it's not biased towards people. This leads us down to our 3 main principles that we need to think about when we're designing an experiment. So the first one, we need to make sure that we are using enough subjects. Okay, make sure that you have enough subjects in each group to reduce variation in the results. If one group only has 10 people and another group has 78 people, that's a pretty wide gap. It's going to be too much variation, too much spread. The second thing, you need to make sure that you randomize and use impersonal chance to assign subjects to treatments. Don't pick people personally. Let randomization do it for you. The third thing, control the effects of lurking variables on the response. So make sure that you're using a comparative design, meaning multiple tracks, usually with a control, and ensure that the only difference is kind of this systematic change that hopefully isolates the treatment or the variable you're interested in. That's what good experiments will do. Now at the bottom, we'll get to this a little bit later in the year. If we start to notice that one group in particular has a large change, they're different in their outcome, we would call that difference being statistically significant. It's a significant enough of a change, a difference, that it's probably due to the treatment that we're exploring. So keep that in the back of your head as we kind of move forward. It'll come back towards the end of the semester. Hopefully that makes sense. We're going to look at the last page of the notes and kind of go through an example there that reinforces these ideas. Overall, if you have the option, just remember that experiments will always beat observational studies. There's more depth to them. There's more of a conclusion that you can draw about the variables that you're interested in. Observational studies just say maybe something's going on, but experiments can prove that there is something changing as a result of your treatment. So experiments are a little bit better than observational studies. Question 10. Can aspirin help prevent heart attacks? So the Physicians' Health Study was a big study. It's usually called the PHS. And it was a large medical experiment involving 22,071 male physicians, so male doctors. And it attempted to answer this question: can aspirin help prevent heart attacks? So one randomly selected group of 11,037 physicians took an aspirin every other day. The rest took a placebo. After several years, the study found that subjects in the aspirin group had significantly fewer heart attacks than the subjects in the placebo group. The PHS is one of the most noted clinical trials, actually, of recent history. This has informed a lot of doctors' decisions when talking to patients. Now, not long after the PHS announced convincing evidence that regular doses of aspirin can reduce the rate of heart attacks, at least among kind of this group of middle-aged men that were in their experiment, another study came to the opposite conclusion. So questionnaires were sent to 22,781 residents of a California retirement community. And then of the 61% who responded, they were followed for 6.5 years. Finding of that study, of that survey, was that those who used aspirin daily didn't have many fewer heart attacks and did have more forms of other heart disease than those who didn't take the aspirin. So you have these two conflicting results. Now, which study would you trust more? Why would you believe this? How are you going to defend your argument? And then think about some of those principles that we just talked about: control, randomization, using enough subjects, and things like that. So take a minute and maybe jot down a few answers, a few thoughts that you have. There isn't necessarily one right answer, but there are pros and cons for the two different studies. So I'll pause here for a moment. And if you'd like to pause the video, go for it. Hopefully you just had a moment to think of some comparisons between the two studies. Now, which one should you probably trust more? I would argue that the PHS is probably a little bit more trustworthy. And that's because it was an experiment with a treatment, and it wasn't just this observational study. So the other one, with the California retirement community, they just sent out questionnaires. They were just gathering data. Now, I will admit they had a lot of people. They actually had a little bit more than the PHS study did, 22,781 versus 22,071. But by that point in time, you get a lot of people. It just means that both studies have quality data. Now, unfortunately, that second study from California, only 61% of people responded. That actually introduces bias, if you remember from the last chapter, of potentially leaving sorts of groups underrepresented. So maybe certain ethnicities didn't respond. And so that would make your answer and your data biased against them. It's also maybe not great because this is, again, a retirement community. So these are all older people. Does aspirin have an effect on younger people? We don't really know from that data. And that's one of the drawbacks of the male physician study as well. The typical age for a male physician is kind of somewhere probably in your 40s, 50s, 60s. And so, again, you kind of are losing this segment of your population. This might not talk about younger doctors or younger males, and it might not talk about older males. And that brings up my last point. We don't know how this impacts women. Maybe men and women react a little bit differently just because of biology or some of the differences between guys and girls. So all of those things are kind of things to take into consideration. So what I'm showing up here on the screen, not necessarily something you have to have written down word for word, but these are all things that you might want to consider and have in your back pocket if you have to argue between the two. I'll go ahead and scroll up here and read the last little paragraph. The New York Times quoted the director of the PHS. It was Dr. Charles Hennekins of Harvard Medical School, and he said that the California authors kind of went beyond the ability of any kind of study to draw the conclusions that they did. You cannot draw cause and effect conclusions from an observational study. Only experiments really do that. He also said that in doing such studies, it's crucial to control for the reasons why someone would choose to take aspirin regularly to avoid unintentionally skewing the results. So such a bias for why people take aspirin could result in, say, they were taking it because they were heavier, they were overweight, they were taking it because they smoked more cigarettes or had higher blood pressure. So there were those underlying conditions for why they were choosing to take aspirin. And if those things weren't controlled for, it might make it look like aspirin was causing an effect on increased heart attack risk, when really it was these other things. Hopefully these notes kind of reveal a little bit about experimental design. Now this is still basic experimental design, and through the rest of the chapter we're going to start to build on top of this, talking about different ways to manipulate treatments or to split up individuals and things like that, that real-world experiments are potentially a lot more complex than what we've talked about up to this point. So this should give you enough knowledge to work on your homework, so please be doing that. And thanks for watching, guys. We'll see you next time. Take care.